for section 5.2, which is over integration by substitution. So we're going to continue taking integrals, antiderivatives, and definite integrals, right? We've been using that language to represent the same thing of taking the antiderivative. We're going to use a new technique here, and that's called U substitution. And so what this U substitution is, remember when we're taking antiderivatives, we're looking at something and thinking, what function has this thing I'm looking at as the derivative? Right? So when we're taking antiderivatives, when we have to use this U substitution, this is going to allow us to sort of undo taking the derivative using a chain rule. Right? So when we're looking at something and we think this thing we're looking at maybe used a chain rule to take the derivative and get to it, to undo that and get back to before the derivative was taken, right? To take that antiderivative, we're going to use U substitution. So U substitution is just undoing the chain rules. Integration, antiderivatives, where we're undoing the chain rule. Okay, so what does that kind of look like? Well, we already know how to take the antiderivative of something like this. That's what we were doing in 5.1. But what if it looks like this, right? It's definitely not the same. It doesn't conform to any of our rules that we learned for taking antiderivatives. And in fact, this function on the inside of this integral is something where you would have to take a chain rule to get to it. And so to undo it, to take the antiderivative, we'll use this U substitution. And that is this new technique that we're going to use. Okay, so for something like this, we're going to use U substitution. So what does that even mean, right? So what that means is we're going to define a new variable U to just be something that's got x in it, right? So U is a function of x, where we're going to write U equals and then a bunch of stuff with x in it. And we're going to do this purposefully and sort of intelligently, so that when we can substitute everything in, it makes things nicer, right? You don't want to just define U to be something random or whatever that's not going to help, right? We want to define U in a way that's helpful, so that when we substitute it in, right, we'll substitute U into our integral, then it's going to turn our integral into something that looks like stuff we did in 5.1, so it's going to turn our integral into something we know how to take the antiderivative of, right? So our goal is to choose a U so that when we substitute it in, we're able to take the antiderivative with respect to U, not with respect to x. What does that look like? Well, in this case, what we want to do is let U be all the stuff that's being raised to that 10th power. Right? So that's the guy that'll be helpful here, right? If we choose anything else for U, it's not going to be very helpful. So we want to let U be that x cubed plus 1. Right? Then, where that x cubed plus 1 is, we can substitute in a U. Right? When we do that, we'll get the integral of 3x squared, right? We can't change that. We don't know anything about it. But then this will be U to the 10 dx. Right, so we'll substitute in that U is x cubed plus 1. So we get a U to the 10. Now we want to take the antiderivative with respect to U, so that means that right here, instead of a dx, we're looking for it to be a du. Right? Remember that dx tells us the antiderivative with respect to x. But if we're doing this U substitution, our goal is to take the antiderivative not with respect to x, but with respect to U. So we want to be able to substitute in something for dx where it's going to have a du and allow us to take that derivative, antiderivative with respect to U. So how do we force that dx to become a du? Well, what we're going to do is come over here to where we have U equals x cubed plus 1 or whatever it might be, and you want to take the derivative of U with respect to x, right? And so that symbol du dx stands for the derivative of U with respect to x. So that's what you would get on the left side of that equation. On the right side, take the derivative with respect to x and see what you get. Well, we get 3x squared. Now we're going to do something we haven't done before, and that's play with this symbol du dx, right? And we're just going to pretend that we can separate that du and dx and sort of treat them as their own little things. And then we can solve for dx so that we can substitute in over there. Right, so what do you get when you do that? If you solve for dx, you get dx is du over 3x squared. So now what we can do is we can take this dx is du over 3x squared and substitute in for dx. Right? So what do we get? Oops, I forgot an equal sign. All right, bring that along. The 3x squared out in the front doesn't go away. Can't change that. The u to the 10 is still there. But now instead of a dx, we're going to substitute in du over 3x squared. And again, that came from taking the derivative of this equation with respect to an x. And on the left side, we got a du dx. And on the right side, we got something with an x in it. Then you solve for dx, substitute it in. And now you can see that we have that du in here like we wanted. And what's nice, right, because we chose the nice, the helpful thing for you, this 3x squared is going to cancel. And we're left with nothing with an x, right? Just a u to the 10 du. All the x's are gone. All we have left are u's. We have a du, so we can take the antiderivative with respect to u. And this is something that we already learned, right? Remember, you do 10 plus 1 is 11, so that's u to the 11 over 11. And then since this is an indefinite integral, or an antiderivative, we do a big plus c at the end. So there, from here to here, we took the antiderivative with respect to u. We got u to the 11 over 11 plus c. But that's not our final answer, right? We did take the antiderivative, but we want to write that back in terms of x's, right? This all started with x's, and so we want to finish that with x's. And to do that, we're going to plug back in this x cubed plus 1 for u. Right? So instead of u to the 11, we'll write x cubed plus 1 to the 11 over 11, and then plus c. All right, and there it is. That is our antiderivative of this guy, the integral of it, however you want to say that. That's what it is, and we use this u substitution to do it. So this will be about the same process every time of choosing a helpful u and then substituting in dx, and then all the x's will hopefully cancel nicely like they did here. One thing to note that's just like before in 5.1, we can check our answer by taking the derivative. And you'll notice that in order to take the derivative of this answer and sort of work backwards to see if this is what we get, this stuff in here, you'll have to use a chain rule, right? So I want you guys, if you're watching the video, you can pause it for a second, take the derivative of our answer, which I'll box here, and see and make sure that you get the thing we started with up here, right? If you ever go through this process and take the derivative of what you're saying is the antiderivative, if you don't get back what you started in here, then you must have made an error somewhere, right? So we can always check our work by taking the derivative and seeing if we get back what we started with. Here's another example. So this time, again, notice that it doesn't look like the stuff we've been doing in 5.1. It's a little bit different, and so we'll have to use a u substitution to find this antiderivative. Right? So the first question, right, or the first thing we do is recognize we're going to need to do a u substitution in order to take this antiderivative. The second thing to do is to figure out, what do I want u to be, right? What choice of u will actually help me in this situation? So this time where I've got a fraction, right, it's a quotient, I'm going to take u to be that whole denominator. Right? So I'm going to let u be all of that thing, 3x squared minus 2x. So I'm going to choose that for u. And then I'm going to want to kill off this dx and get it instead to be a du just like before. And the way I do that is take the derivative of this thing with respect to x. On the left side, the derivative of u with respect to x is just that symbol du dx. And the derivative of 3x squared minus 2x with respect to x is 6x minus 2. Right? So if you're paying special attention, you might notice that, hey, that's already there. And that's really good because that means this choice of u is going to help us because it should cancel. Right? So that was why we chose this u, is because we identified that if we let this thing in the denominator be u, its derivative is going to show up and it will cancel when we do the substitution. So again, we want to solve for dx, and we get dx is du over 6x minus 2. And once we have u equals and dx equals, we're going to substitute those into our integral and see what happens. So we get a 6x minus 2. Instead of over 3x squared minus 2x, it's just over u. And then instead of a dx, we get du over 6x minus 2. All right, now the nice thing here is that since we're multiplying, this 6x minus 2 in the numerator and denominator cancel. And we're left with just the integral of 1 over u du. Right, so now what's the antiderivative of 1 over u with respect to u? Well, remember from last section, that's the natural log of the absolute value of u plus c. All right, so there it is. We took the antiderivative. Again, like I was talking about in the last video, notice that once I took that antiderivative, I stopped writing these integral and du symbols, right? Now, just like before, I started out with x's, so I want my answer to have x's in it, not u's. So I'm going to substitute in what I let u be equal to, and I get 3x squared minus 2x plus c. Okay, now, how could I check that this is the correct answer? Well, I could take the derivative of it. If you took the derivative, you'll get 1 over 3x squared minus 2x times the derivative of 3x squared minus 2x, which is 6x minus 2. And hey, that's exactly what we started with up here. And that is a double check that our antiderivative that we're saying is correct is actually correct. Let's look at another example. So this time I've got an exponential, right? So instead of a fraction or polynomial type looking thing, I've got an e to the something. Right? So anytime you see that e to the something, the helpful guy is going to be to let u be that exponent of, in this case, it's x squared minus 1. Right, so let's let u be x squared minus 1. So we'll substitute that in. In order to get rid of this dx, we are going to take the derivative of this equation with u's and x's. On the left side, we get the derivative of u with respect to x, so that's du dx. On the right side, we get 2x. Now solve for dx, and you get dx is du over 2x. Now we're going to substitute in u instead of the x squared minus 1, and du over 2x instead of the dx into this integral, and we get the 2x hangs out for now. Instead of e to the x squared minus 1, we get times e to the u. And then instead of dx, we get du over 2x. And now again, you can see that what's nice here is that this 2x will cancel, and we're left with the integral of e to the u du. So what's the antiderivative of e to the u with respect to u? Well, that's just e to the u plus c. Now again, we started out with x's up here, so we want our final answer to have x's in it. So substitute in what you let u be equal to, and that was an x squared minus 1. And then the plus c just hangs out. And there's our answer. That's the antiderivative. Again, we could double check this by taking the derivative and making sure we get what we started with up here. What's the derivative of e to the x squared minus 1 plus some number? Well, the number goes away, that plus c, and we're left with e to the x squared minus 1. And then chain rule says multiply by 2x, and that's what you started with, right? So again, we use this u substitution to take the antiderivative and undo the chain rule. What's really important with these u substitutions, like I've said, is to first identify that what you're looking at is going to take a u substitution in order to find the antiderivative. The next most important step is to identify what you want u to be equal to so that it'll help you when you substitute things in. So here's that strategy for what you should let u be equal to. All right, what do you want u to be? So the first thing, this is like our first example. If the integral involves a power, so we had like a bunch of stuff to the 10, or a radical, let's say it was a cube root of a bunch of stuff, then you want u to be either whatever's being raised to the power or all of the stuff inside of the radical. Right? So I use these powers and radicals together because you can always rewrite, remember, like a square root as to the 1/2. So these really are sort of the same scenario. So anytime you have something like that, you always want to let u be the stuff that's being raised to the power or the stuff that's inside the radical. All right, in our second example, we had a quotient, right? It was a rational function, something divided by something else. Right? Remember, in that case, we didn't have something like some stuff divided by something to a power. Right? If you see this, that goes up here with this example. Right? And you want to let u be what's in there. If you see something where it's stuff divided by and then just something, and the power here is just a 1, or there's nothing, and it's just some stuff over something else. Right? This is like our second example. In this case, you want to let u be that whole denominator. Right? You want to let u be the whole denominator. This example will always turn out to be a natural log. Right? Because we're going to end up taking the antiderivative of something like 1 over u. In our last example, we had an integral that involved an exponential expression, something like e to the stuff. And in that case, you always want to let u be the exponent, right? Let u be all that stuff up there. And that's going to be the u that'll be helpful. Okay, so with this in mind, let's do some more examples. How about the antiderivative of x over 1 plus x squared dx? Right, so which one of these does that look like? On the last slide, we had 3 examples. I'll give you a second to think about it. All right, so that's going to be that second example where we had a fraction and the denominator was not all raised to a single power, right? It's just something and there's no power there, so that power is like a 1 hiding there. However you want to think about that. Since it's a rational function, right, a quotient, something divided by something else, and the thing in the bottom is not all raised to a single power, right? We have a power with an x squared, but not the whole thing squared. So in this case, we want to let u be that entire denominator, 1 plus x squared. All right, now we're going to do the same steps as before to try to substitute this dx. So we'll take the derivative of this guy with respect to x. On the left side, you get the derivative of u with respect to x, which is du dx. And on the right side, you get 2x. Now solve for dx just like before, and you get du over 2x. And so we're going to substitute in u for the 1 plus x squared, and du over 2x for dx. When you do that, you get the integral of x stays, right, over u, and then instead of a dx, you get du over 2x. Right, now here, the x's cancel, but that 2 stays around, right? So what are we left with? We have the integral of that over 2 is the same as a 1/2, right? 2 in the denominator, times 1 over u times du. So now we're going to use our properties of integrals to pull this constant 1/2 out. And that's the same thing as 1/2 times the integral of 1 over u du. So what's the antiderivative of 1 over u du? Well, that's natural log, so the 1/2 comes along for the ride, and you multiply by the natural log. Don't forget to do the absolute value. And then this is an antiderivative indefinite integral like we've been doing, so we always have to do plus c, right, for that plus some random constant. So there's our antiderivative. Again, we started with x's, so we want to finish with x's, so let's substitute back in u equals 1 plus x squared. And there's our answer. Again, I do expect you guys on your own to check this by taking the derivative and making sure that you get back what you started with up here. For example, this time we have 2x squared dx over 5 plus x cubed cubed. Right, so whether or not that dx is in the numerator, it doesn't matter. Right, I just want to show you guys that this is another way to write the same thing, where instead of the dx being off to the side, you can just stick it in the numerator. And if you see that in your homework, you should know that this is another way to write that. It's the same thing. Okay, so which one of the three things that we talked about does this look like, right? What do we want u to be here? So first, of course, we should recognize that this is going to take a u substitution. So it doesn't look like the simple stuff we were, simply written stuff that we were doing in 5.1. So what do we want u to be? Well, we have a quotient still. It's something divided by something else. It's a rational function. But this time that whole denominator is raised to a power. 5 plus x cubed. It's all raised to a power. So we don't want to take the whole denominator, but what we want to do is take the stuff that's being raised to that power. So in this case, we want u to be 5 plus x cubed, because that's the thing that's being raised to the 3. All that stuff is being cubed, so that's what we want u to be. All right, so now to solve for this dx, to get it out of here, or this dx, however you want to write this, we need to take the derivative of this guy with respect to u. With respect to x. When you do that, you get the derivative of u with respect to x, which is du dx. Now, what's the derivative of 5 plus x cubed? Well, that's 3x squared. So now we're trying to get rid of this dx, so we need to solve for dx. And when you do that, you get du over 3x squared. So now we can substitute in u for 5 plus x cubed and du over 3x squared for dx. When you do that, what do you get? You get the integral of 2x squared over u cubed, and then du over 3x squared. So we substitute in du over 3x squared for dx, and u for 5 plus x cubed. Now again, we have some stuff that cancels. The x cubes cancel, but our 2 in the numerator and our 3 in the denominator both hang around. And we can pull that constant 2/3 out and say this is the same as the integral it's 2/3 times the integral of 1 over u cubed du. Now, in order to take this antiderivative, what we need to do is rewrite 1 over u cubed as u to the negative 3. Now, to take that antiderivative with respect to u, we're looking at what's the antiderivative of u to the negative 3 with respect to u. So remember, for that, you bring this constant 2/3 along for the ride, and you say, what's negative 3 plus 1? Well, that's u to the negative 2. And then you divide by that negative 3 plus 1, which is negative 2. And then you can do a big plus c. Alright, so remember when we were taking derivatives, I never required you to simplify anything. I don't really mind if you don't simplify this. If you left it like that and you didn't cancel these 2's, that's okay. But you certainly have to, again, rewrite it, final answer with x's in it, right? So whether you write it as 2/3 times something over negative 2, or if you want to cancel these 2's, that's okay. However you want to do it, it's something like either negative 2/3 times something over 2 if you keep this guy around. Or you can cancel it. Whatever. That's not the point. The point is we need to be plugging in 5 plus x cubed where that u is. So we're going to do 5 plus x cubed and then u to the negative 2 plus c. And that's our answer. Again, you can double check by taking the derivative of that answer and making sure that you got what you started with, which was the stuff up there without the dx. I will note that you could also start this problem by rewriting this denominator to have to put it in the numerator. Right, so we'll note another way to do this, right? You can always do things more than one way. One way to do this would be to rewrite this as 2x squared times 5 plus x cubed to the negative 3. And then do all the exact same steps from there. But it's just bringing that into the denominator with a negative 3 first, as opposed to waiting to do it down here when we brought it up. Right? Either way is fine. It's all the exact same steps, just a different order. Whatever you like most as you start practicing this, maybe try it more than one way. Do it that way, right? Whatever makes it easiest for you. Okay, how about the integral of 3x e to the x squared dx? Right, so this one has an e to the something in it, so you always want to let u be whatever that exponent is, and in this case that's x squared. Right, so we're going to plug u in for x squared. In order to get rid of this dx, we're going to take the derivative of this thing with respect to x. On the left, you get the derivative of u with respect to x, which is du dx. And on the right, you get 2x. So now let's solve for dx, and you get du over 2x. And so we're going to plug in, instead of an x squared, a u, and instead of a dx, a du over 2x. So when we do that, what do we get? We get the integral of 3x e to the u, and then du times du over 2x. All right, so there we go. We notice here that this x cancels with this x, and we're left with, well, we still have a 3, and we still have a over 2, but we can pull those constants out, and we're left with 3 halves times the integral of e to the u du. And what's the antiderivative of e to the u with respect to u? Well, that's just e to the u. So you're left with 3 halves e to the u plus c. All right, and our last step here is to substitute in, and we don't want our final answer to have a u in it. We want our final answer to have an x in it. So we'll substitute in x squared for u, and there it is. That's our answer. I guess I lied. That's not quite the last step. Really, I want your last step to be taking the derivative of what you say is the answer and double checking that you get this. But I'll let you guys do that on your own. Okay, let's look at another example here, right? So we've covered all the basic steps where things canceled very nicely, but what if they don't exactly cancel perfectly? Or what if you don't even know that that's going to happen, which it will here? You're going to do all the same steps as before, right? So we've got something that's raised to a 7 right there. So that's what we're going to look at to do a u substitution. So first, notice that this does look very different than what we've been doing, right? It doesn't look like just x to the 7. It looks like something different. So we have to use u substitution to take this antiderivative. And again, this is like that first thing on our list where we have something to a power. So we want to let u be all of the stuff inside those parentheses that's being raised to that power. So we'll let u be x minus 2. All right, we're going to substitute that in. We also need to get rid of this dx. So to do that, we take the derivative of our equation with u's and x's. On the left side, we get the derivative of u with respect to x, which is du dx. And on the right side, you just get 1. So what does that mean? Well, that means if when you solve for dx, you get dx equals du. So now we can substitute, instead of a dx, we'll just say dx is the same as du, so you can just write that in there. And instead of x minus 2, we're going to write u. So let's write the integral of x plus 2, and then it's u to the 7 du. Okay, so notice that things didn't exactly cancel perfectly. So how do we fix that? How do we get this x right here to go away? Well, what we want to do is turn that x into a u somehow. Right? We're trying to take the antiderivative with respect to u, du. So what we're going to do is go over to this guy and solve for x. When we do that, let's see what we get. We get a x equals u plus 2. So we can now look at this x and substitute in u plus 2. When we do that, we get the integral of u plus 2 times u to the 7th du. And now that only has u's in it, so that's good. And you may think, well, how is this any better than what I started with? Right? It looks similar. Well, what's nice about it is that the thing that's being raised to the 7th is just a u. So we can distribute it nicely and see what we get, right? When we do that, we're going to distribute. You get the integral of u to the 8, right? U times u to the 7 plus 2u to the 7 du. And that you should recognize as something that we were able to take the derivative of in 5.1. Notice if you tried to distribute things here, you'd run into a problem, right? That's not so easy. You can distribute it, but then you're still left with something that you don't know how to take the derivative of. Whereas if you do this u substitution and then do your distribution on this step, you are able to distribute it and get something that you know how to take the derivative of. I'm sorry, I said the derivative twice there. I meant antiderivative, of course, but you all probably caught that. So let's take this antiderivative. Again, it's with respect to u, so u to the 8, well, remember you add 1 to the 8 and you get 9, so u to the 9 over 9. Plus 2 times, and then u to the 7 plus 1 is u to the 8 over 8 plus c. And just like we've been doing, our last step is to rewrite everything in terms of these x's. Right? So what do we get when we do that? We get x minus 2 to the 9 over 9 plus, and again here, I don't care if you simplify, if you want to leave it as 2 over 8, or if you want to write it as just over 4, that's fine. What's important is we need to substitute in this x minus 2 instead of u, so we get x minus 2 to the 8 plus c. And there is our antiderivative. Again, you should double check that this is the antiderivative by taking the derivative of this guy and seeing if you get this as your as the derivative. When you do that check, one thing to notice is that you'll have to rewrite it to make it look exactly like what we started with. So check that and make sure that you see what I mean by that. If not, make sure you ask me in class. Look at our penultimate example here. What do we have? So we have e to the 2x over e to the 2x plus 1. Take the antiderivative with respect to x. How do we do that? Right, so at first glance, you might think, oh, this has e's in it. Let's let u be the thing in the exponent. That was one of our rules. However, in this case where there's two e's that show up, one in the numerator and one in the denominator, that's not going to be helpful. Right? You can do it and rewrite it, but you'll still end up with something you don't know how to take the antiderivative of. What we want to do here is use the rule where we have a quotient and we take that whole denominator and let u be that whole denominator. So let's do that. Let's let u be that entire denominator. And then we want to find dx, so we'll take the derivative with respect to x. You get du dx on the left On the right, what do you get? Well, you get e to the 2x times 2 plus 0. So solving for dx, you get dx is du over 2e to the 2x. And now when you substitute everything in, what do you get? You get the integral of e to the 2x over u times du over 2e to the 2x. And because we let u be the entire denominator, that e to the 2x showed up in the derivative, and so we can cancel it. And we're able to get just 1/2 the integral of 1 over u du, which is something we should recognize. So we know how to take the derivative of that. What is it? It's 1/2 the natural log of the absolute value of u plus c. Okay, so we were able to take the antiderivative by letting u be that entire denominator. If you had let u be this 2x up here, then you would have been stuck with something you still didn't know how to take the antiderivative of, and you would have not been able to go any further. So if you don't recognize immediately to let u be that entire denominator, and if you do let it be the thing in the exponent, that's okay. You should pretty quickly realize that it's not going to be helpful, in which case you should backtrack and choose the whole denominator instead of the exponent. All right, our last thing to do here, of course, is to substitute back in our u equals stuff with an x. When we do that, we get the natural log of the absolute value of e to the 2x plus 1 plus c. All right, and that is our antiderivative. You should check that that is the correct antiderivative by taking the derivative using a chain rule and seeing if you get what you started with up here. Okay, our last example, how do we do something like this? We have the antiderivative of the natural log of x minus 2 over x. What can we do there? Well, we definitely have not learned how to take an antiderivative of natural log of x, right? We've not talked about that. That's not something that was in our rules from 5.1, and it's not showed up yet here in 5.2, but there it is. So, if we don't know how to take the antiderivative of natural log of x, it's a good idea to try to kill off that thing by letting that be in what you set u equal to. And so what do I really mean by that? What I mean by that is whenever you see a natural log of x and you're trying to take the antiderivative, you're going to want to let u be whatever piece has that natural log in it. So in this case, we want to let u be the natural log of x minus 2, and that way we'll be able to substitute in and have that natural log disappear so that we can actually take the antiderivative. All right, so now we need to do just like we've been doing and find the derivative of this piece with respect to x, and we get 1 over x. So solving for dx, you get du, and then over 1 over x, that's times x. Now substitute everything in there, and you get the integral of, well, the natural log of x minus 2 is just u over x times du times x. And here these x's cancel. So hey, that's nice. That's what we wanted. And we're left with just the integral of u du, which we know how to do. Right? So when you see this natural log and you're asked to take an antiderivative, you want to let u be that entire piece that has the natural log. That way it goes away and you're able to take the antiderivative. So we don't know how to take the antiderivative of natural log. All right, what is this antiderivative of u du? Well, that's really a u to the 1. So we raise that exponent by 1 to 2 and divide by 2 and then add c. Our last step, of course, is to substitute in what u is in terms of x. When you do that, you get the natural log of x minus 2. All of that squared over 2 plus c. And you can and should double check everything from 5.2. I still have the whole list for you guys like I did in 5.1. This is very important to get a lot of practice in. Make sure you come to class with any questions that you have over the notes or if you try the homework. And I'll see you then.